Yeah, good afternoon, students. So today, the continuation of the polarization by reference topic we will discuss. Polarization due to double refraction. So in previous class, I have been discussed about the calcite crystal. Whenever a unpolarized light which is passing through the calcite crystal, there should be two rays which are emerging out from that crystal. So one is along with the principal axis, another which is going to be makes a certain angle, and which is also going to be coming out from the crystal. The thing is that here two rays which are emerging. One is the ordinary, another one is the extraordinary. So the thing is that here extraordinary ray which is passing emerging out along with the principal axis, and only ordinary ray which is going to be makes an angle and which is coming out. So when you observe the two emergent rays which are coming out from the calcite crystal, both these two are parallel to each other. That is the thing. Okay. So in this, a double refraction crystal, like Iceland spar, calcite crystal, they refracts incident light into two different paths. So if an object is viewed by looking through the crystal, two images are seen. So what type? Double refracting crystals. So polarizing filter can be used to completely block one image. So two rays are formed because they have a different speeds due to the two refractive index planes in the medium. So you can go for it. That is both beams. Uh, Here they have been formed a polarized. So you can see that here extraordinary, ordinary. But this is unpolarized light. So whenever it is passing through a calcite crystal, which is a double refracting, so emerging rays which are one to another, they have been uh, parallel to each other, and one parallel to the surface and other perpendicular to the surface. Okay, so this is the case. Next, polarization by the dichroism. Uh, this concept is by selective absorption. Such crystals which are used to transmit wave whose electric field vibrates in a particular plane and absorbs electric field vibrating in another. Okay. One plane electric field is vibrating, and in other plane this field vibrations which are to be absorbed. So such crystal is tourmaline polarite. So what do you mean by polarites? So yesterday we already discussed the most common method of polarizing involves the use of the polarites. Uh, there is a long chain of molecules which are aligned within the filter in a particular direction. When an unpolarized light falls on a polarite, what will happen? Unpolarized light. So the electric component, the electric vector, which is oscillating in the direction of the alignment of the molecules of the polarite, which is observed, and the same thing, which is perpendicular to the direction of the alignment of the molecules, pass through the polarites. Two things you have to observe. So the transmitted light is plain polar. So you can see the relationship between the long chain molecules orientation and the orientation of the polarization. So we can see here when a molecule in the filter are aligned vertically, molecules are aligned vertical. You can see. Don't observe the red line. The polarization is horizontal. Here Molecule filters which are aligned horizontally, the polarization is vertical. So dual filter are polarizer and analyzer. So if the transmission axis of the polarizer and analyzer which are perpendicular, then no light is transmitted. Okay. Polarizer and analyzer are perpendicular, no light is transmitted. The light transmitted at the other angles follows the law of Malus. And these two, polarizer and analyzer relation, can be best described by Piquet-Fiance analogy. This is the, according to his, both fences are aligned in the vertical direction. These two, first one, second. So a vertical vibrations can make through it both the fences. Other one is the parallel, another one is the horizontal. So here the vertical vibrations which makes it through the first phase fence will be blocked here. So this is the Piquet-Fiance analysis. So law of Malus. So here when a beam of completely plane polarized light which is incident on an analyzer, the resultant intensity of light capital I transmitted from the analyzer and varies directly at the square of the cosine angle between the plane transmission and analyzer and polarizer. So I is proportional to cos square theta. I equals to I naught cos square theta. What do you mean by I naught? Intensity of the polarized light. So which is the half the intensity of unpolarized light incident upon the polarizers. Yesterday we discussed that. When unpolarized light which is passing through a polarized, then the intensity of the unpolarized light which is to be reduced. How much? 50%. So here the intensity is maximum if the transmission axes are parallel and intensity is zero if the transmission axes are perpendicular to each other. You can see the first diagram which is indicating here. This is unpolarized light. So which is passing through analyzer and polarizer. Both are parallel to each other. Okay. So the intensity of the unpolarized light will be reduced. Whereas in the second figure, polarizer and analyzer both are perpendicular to each other. Then no light of the unpolarized light will be emerging out through this polarites. So what are the applications of the polarization of light? So these are the polarites, glass spectacles. So unpolarized, polarized light by reflection. So where you are using in polarized sunglasses. Light reflected off a pool of still water is partially polarized parallel to the water surface. And this may gives to the a glare and the transmission direction of polarized sheet in the sunglasses is vertical, which blocks horizontal components. So like that here, it may be reducing the intensity of the light and glares. See here, fishermen use polarized sunglasses to locate fish underwater without using polarites. Directly, if you observe, the fishes in the river should appear like this. Whenever if you use a polaroid sunglasses, it can easily shows that where the fish is located in the river. See the difference. Okay. Next, without polarized sunglasses, in the night they appeared like this. By using the polarites, it may look like. Is it clear? So in photographic filters also, so glare caused by reflected light of water surface makes it harder to see behind water. So photographers often use filters to cut out glare and get better pictures. See here, when no filter is used. So in sea, how the fish is going to be look likes to the observer. When a filter is used, then the fish which can be visible like here also. Any specimen in glass cases can be well photographed by using filters. This is unpolarized. If you use no polarites, this is the case. Vertical polarizer, this is a horizontal polarizer. So next is the applications of the polarizer. Decoration. In Titmus stereo test, then Titmus flight test. Next, photographic secret, capturing by vivid blue sky using Polaroid. So this is the case. Horizontal, vertical, if no polarites. So polarization by the birefringence. In birefringent biprisms, such as a Nicol, Glan Foucault, and Walston, which are used to produce the polarized light. So this is unpolarized light. So this is Nichols prism, extraordinary ray which is passing through the Nichols prism along with the optic axis, and ordinary ray which may passing and emerging out, which makes an angle theta with the direction of the principal axis. And there is a deviation between E and O. Okay. So this is the Walston prism. LCD, liquid crystal displays. There are some crystals uh, which become aligned when the electric field is put across them. opt image of the retina. So Snellen eye chart. So special polarizing glass which may be used here. So here OD polarized at 90 degrees and OS polarized at 180 degrees. Test one eye at a time through patient viewing by binocular. Alternating line of optotype are also polarized at 90 and 180 and used to detect melanin. Mineral concentration. So this is the case. Other applications. So they actually this is not in our syllabus. In 3D films also. I think so. Most of the films which are uh, giving in 3D, there only you cannot able to watch the movie in theaters. Why? Because of which is a 3D. If you without wearing the 3D glasses, that should be blurry. Whenever you if you use a 3D Polaroids, so here two films shown at the same time through the two projectors. So projected through polarizing filters with axis perpendicular to each other. And here viewers wear glasses with two polarized filters with the axis perpendicular. Left eye sees the movie projected from the right. Right eye sees the movie projected from the left. And this gives viewers a perception of depth. 3D films. See here. Avatar. It's the bench. Universe. And photoelastic elasticity. Stress analysis. This is the stress analysis. This is stress analyzer. Saturimetry. This is the Laurent offset polarimeter. This diagram. Measuring the concentration of sugar solution. Sugar in a solution. And due to the molecular structure of sugar, this solution rotate the plane polarization as light passes through the saturimeter. This one. This is Lorentz offset polarimeter. Unpolarized light. This is a vertical polarizer. This is analyzer. So when it's sugar solution, the polarized light may be deviates. And again, if it is passing through the analyzer, the intensity of light is to be reduced. And by using the camera, he can able to capture. Inset lamp and ophthalmoscope. Okay. So while you are going to eye checkup, there only you can able to observe this. So these are the simple questions. Optically active substances are those substances which dash Okay. So these are the outlines for the polarization. Now I can give you uh, in detail we will discuss. 1 minute. So law of Malus. So let us examine what happened to the intensity of light, which is emerging out of the analyzer. Okay. So there should be a polarizer as well as the analyzers. As the analyzer, which is rotated about the direction of the propagation of the light. So in this, the intensity which is a zero when the two polarites are crossed. That means one is parallel, another one is the vertical, means no light is emerging out through the polarizer analyzer. So that there is no intensity of light which is coming out from that. That's why we can say that intensity is zero. When polarizer as well as the analyzer both are parallel to each other, then the intensity of the light which is passing through the polarites, then the intensity may be reduced by 50%. That is the thing here. When the angle between the two polarizer directions is 90 degrees. Okay, that is 0. So you can able to observe that the intensity is maximum when the angle is 0. That means those are parallel to each other. Which one? Parallel for polarizer and analyzer. So for any other angle, theta, if the amplitude of the plane polarized light falling on the analyzer, which is extraordinary, and the amplitude of the light that emerges is E cos theta, where theta is the angle between the polarizer and polarizing direction of the analyzer and the polarizer. So you know pretty well the intensity means square of the amplitude. The amplitude is here cos theta. So I equals to Im cos square theta. Im is the maximum intensity of the polarized light. So which is called law of Malus. So important shortage. Next, polarization by reflection. So the French physicist Malus has been discovered when ordinary unpolarized light is incidenting at an angle of about 57 degrees on the polished surface of a glass plate. Then what will happen? The ray which is reflected in other direction. So that the reflected light is plane polarized. Okay. So this concept which was demonstrated by the Malus. So you can see the experimental setup which may consist of two glass plates, capital B and C. And the second glass plate C is mounted on a pedestal such that it can be rotated about BC. So in first figure, an unpolarized light beam incident on the first glass surface at B. The light is again reflected at the same angle by the second glass plate C. Okay, where B and C are parallel to each other. Then if you rotate the C about the axis BC, then the intensity of the light reflected by C, which is decreases and vanishes completely at an angle 90 degrees. That is from second figure. So further, if you are rotating with the maximum angle 180 degrees, then the intensity to decrease to zero again 270 degrees and the maximum at 360 degrees. So during this one complete rotation, the angle of incident on the both planes remains 57 degrees. Here the angle of incidence is different from the 57 degrees and the intensity goes through the maximum and minimum every 90 degrees. But the minima will not be go to the zero. In other words, there will be always by reflected beam C. Here the experiment which may be describing that, which may be made clear by examining the change that takes place in reflection. Suppose an unpolarized beam at glass surface, which is described already, the electric vector of the incident light beam can be resolved into two components. Here, these are the dotted lines, which are representing here a reflected, and other one is the refracted from one media to another media. So the angle of incidence is theta p, which is called a polarized angle. Here the transmitted beam partially polarized. The intensity of the reflected plane polarized beam can be increased by using a stack of glass plates. And the reflection successive surface add the intensity. So this is the case. So here the polarized angle theta p, Brewster found that this one, the reflected and transmitted beams which are both are perpendicular to each other. So the theta 1 plus theta 2 is 90 degrees. Theta p polarized angle, theta r refracted angle, both are 90. By using Snell's law, sin A by sin R, that is theta P by sin theta R. Where mu sin theta P can be written as mu 2 sin in place of theta R 90 minus theta P. From this, here we are substituting. Sin 90 minus theta is cos theta. So sin theta by cos theta P, tan theta P. So mu 2 by mu 1. That is nothing but a mu. This equation you can call it as a Brewster's law. Most important short question. Combinedly, they may be asked as a essay question. law of Malus and Brevestus. Next is the double refraction. I will show you one video, so you can easily observe. So here birefringence. We'll go for the birefringence. You can see the which one is the uniaxial and which one is the biaxial. You can see which one is uniaxial here. Isometric crystal is this one. This is uniaxial crystal and this is a biaxial crystal. Isometric means here you can see that Na equals to Nb equals to Nc. Whereas in uniaxial Na equals to Nb, but it is not equals to Nc. Whereas in biaxial, all these three are not equal. You can see the optic axis for isometric crystal. This is a circle, okay, ellipse. Ordinary. That equals to Nie minus NO. Na is the refractive index for the extraordinary ray. NO is the refractive index for the ordinary ray. Okay. So that is about the birefringence and the other one is that I will show you birefringence in a crystals so that you can feel that by observing lively uh, through a video, so you can easily uh, know the definition what it is going to be saying here. Double refraction. So double refraction by Huygens explanation. So according to the Huygens explanation of the phenomena of double refraction, uh, in uniaxial crystals, uh, what are the facts which was made by the Huygens means? In a doubly refracting medium, there are two beams traveling in the crystals. How many? Two beams. Hence, every particle in the medium sends out the secondary wavelets. We know that. And the velocity of the ordinary beam, which is small in all directions. Therefore, corresponding wavelet must be spherical. Whereas the velocity of the extraordinary beam depends on the direction of the crystal. So the ordinary and extraordinary beams travel with the same velocity along the optic axis. So based on these two facts, Huygens has been assumed that extraordinary wavelets to be an ellipsoid, revolution of an ellipse about the axis coinciding with the optic axis. So the velocities of the ordinary and extraordinary ray which are equal uh, along the optic axis. So ordinary and extraordinary waves touch each other in the direction. See here. Inside is elliptical, outside is ordinary. Here inside is ordinary, outside is elliptical, extraordinary. Extraordinary which is in elliptical shape, ordinary which is in circular shape. So where extraordinary as well as the ordinary ray for these two are going to be coinciding. Here it is coinciding, here it is here. Okay. So in calcite crystals, the velocity of light is maximum in the direction perpendicular to the optic axis. Hence, the spherical wavelets inside an ellipsoid wavelets. Such crystals are called negative crystals. Which are negative crystal. In quartz, where the velocity is maximum along the optic axis. So the ellipsoid, which is inside the sphere, ellipsoid, which is inside the sphere. That means this is a positive, this is a negative. Okay. These are the construction, how we are going to construct these calcite crystals based on this. Next is the refractive indices. So it is clear that the discussion presented above, the doubly refracting materials have two indices of refraction, which is corresponds to the ordinary ray and extraordinary ray. That is mu naught and mu e. But there is no difficulty in defining mu naught because of mu naught means sin A by sin R, which is constant. So the index of refraction for the extraordinary ray is a function of direction. So it is a customary to state the index for the direction at right angles to the optic axis, in which the velocity is maximum or minimum. So mu naught is velocity of light in vacuum, the ratio, velocity of the ordinary. Velocity of light in vacuum by maximum velocity of extraordinary wave for negative crystals. So the refractive indices for the extraordinary ordinary ray, which was given for the calcite as well as the quartz crystal. You can observe this. Okay. So the values which may determine experimentally by using the prisms, which are made out of the double E refracting materials, and can determining the angle of minimum deviation using the spectrometer. Another important is Nichols prism. So here, which is a sketch of calcite crystal. Sometimes it may be called as a Iceland spar. So at each of the corner A and B, the angles formed by these three intersecting faces are same. Here. What about each angle? 101 degrees 55 minutes. A line at capital A and B, which are drawn so that it makes an equal angle with the three intersecting edges in the direction of the optic axis. So the direction of vibration of ordinary extraordinary ray can now be specified with respect to the optic axis. So in calcite crystal, it may be contains optic axis and which is perpendicular to the opposite faces of the mirror. So here an unpolarized, a beam of unpolarized light, which is passing through this crystal, which may be splitting into two uh, beams. One is along with the principal axis, another one which is emerging out. So each beam is linearly polarized. So what is the direction of the vibration in ordinary, which is perpendicular to the plane of the principal axis, and the direction of vibration of the extraordinary, which is parallel. So that you need to say that here this is extraordinary ray and this is a ordinary. Okay. So the thing is that if you want to identify extraordinary as well as the ordinary ray, both of them at a time, which are emerging out through the crystal. So one has to be deviate in other direction means here. So the Nichols prism which was made, that means one ray has to be completely vanish in other direction. Only the extraordinary ray has to come out from that along with the principal axis. So that can be achieved. That a calcite crystal may be reshaped by using a either polarizer or analyzer, and this can be achieved by removing uh, one of the polarized rays from the transmitted beam, and the method which is illustrated in above figure here, this one. So here the end faces which are cut so that the angles in the principal section which may be reduced 71 degrees to 68 here, 71 degrees to 68, and as well as the crystal which is then cut into have a long as the diagonal AC which is perpendicular to the plane of the principal axis. This one. This is the principal axis diagonal. So the two halves which are then cemented together with a clear Canada blast. That is a cement. So the optical device which is constructed, that you can call it as a Nichols prism. So the refractive index for the ordinary ray for calcite crystal is 1.66 and the Canada blossom is 1.55. So the angle of incidence of ordinary ray at Canada blossom surface which is greater than the critical angle, so that it is totally reflected, and the index of the refraction of extraordinary ray in calcite which may be depends upon the direction of the propagation. So Nichols prism, the index of refraction of the extraordinary ray which is approximately 1.49, so that there will be a transmitted through the Canada blossom and emerging out from the prism. So Nichols prisms are used in optical devices as an analyzer as well as polarizer. So the light which is transmitting through this prism, which is vibrating in the direction of the parallel to the short diagonal and its end surface. Therefore, the unpolarized light which is incident on the Nichols prism, it may produce the plane polarized light, which the direction is parallel to the short diagonal ends. And this property is which is utilized in producing linearly polarized light. So a plane polarized light with its direction of vibration parallel to its short diagonal. And here it is completely cuts off linearly polarized light with the direction of the vibration perpendicular to the short diagonal. This property used for analysis of. So what is the summary of this polarization chart? Malas law. What do you mean by polarized light? How the unpolarized light which may be converting into a polarized light. Malas law, Brewster's law, polarization by reflection, Huygens theory, double refraction. What is polarizer and what is analyzer? If both are parallel or if both are perpendicular, what will happen? And Brewster's law, Nichols prism, everything we have been discussed. Okay. So, what are the questions? Describe the experimental method to produce plane polarized light by reflection. That is the first one. Nichols prism construction. and applications. Short questions, state and explain malas. Eigen's explanation. So these are the problematic questions. Next is the production and analysis of different types of polarized light. So in this quarter wave plate, along with the half wave plate, production of circularly and elliptically polarized light, direction of polarized light. There is a plane polarized, circularly, elliptically. That is a linearly polarized light is a plane polarized. So circularly polarized light, elliptical. That's it. So by coming class, we will go for this. So by coming class, we will discuss about this quarter wave plate, half wave plate. Okay. Direction of polarized light. So there are most of the questions which are coming out from the polarization only. So there may be two short questions may be asked as an one essay question. Better to remember this. Uh, so here, why? Because of in this very small questions are there. Uh, Concept is very lengthy, but the thing is that here uh, little concepts are there. So by combining two or three, they may be asked as a one essay question. Okay. So by coming classes, we will discuss the continuation. Okay. Right. Thank you. Thank you, one and all. I'm signing off.